Hello, my name is Jordan Kraus, and I'm here to give a short summary and update on some improvements we're making to the ARM SMMUv2 driver, specifically to support the Adreno GPU that is part of most of the Qualcomm Snapdragon SoCs. To start with, we'll do a little bit of history. So the Qualcomm, the Adreno GPU has always had an attached SMMU. Even in the very early days in the A2XX, there was what I call a proto SMMU. It was slot based. It was okay, wasn't great. But then when we moved to the A3XX generation, which is kind of the start of the current lineage of Adreno GPUs, we started with a very customized version of the ARM SMMU. We call it Qualcomm IMMU. And then slowly over time, we evolved into something. It's similar to the MMU500. It's a little bit customized, but it's essentially an MMU500 with a little bit of stuff glued on. The advantage of this is that, you know, as of when we transitioned to A5XX, I guess that was 3 or 4 years, 5, 6 years ago maybe, we were able to start using ARM SMMU driver as it was. So we were able to start using the stock driver. Which works out pretty well, but there are a few quirks that the Adreno GPU has and would like to take advantage of that are not generally something that other GPUs or other clients have. So most clients have a DMA interface. They usually have a one-to-one relationship between their virtual address space and the memory that they're allocating. And for the most part, they are very simple. You create memory, you map it into IMMU, and go on forward with that. The ARM SMMU or the Adreno GPU is a little bit different. So, one of the biggest features that we want to provide for the world are what we call per instance page tables. And we've had per instance page tables or per process page tables as they're often called as part of the downstream drivers since A3XX days. And the object here is very simple. We want to provide individual virtual address spaces for different containers. The name changes a little bit. I call it per instance, but it's also called per process because this can be as granular as a context and as broad as a process. So if you are able to track all the file descriptors and contexts that are part of a process, you could switch the page table for each process and have it available to multiple contexts. For upstream, for DRM MSM, we decided that we're going to go with a file descriptor. So a lot of this discussion will be on a file descriptor basis. The reason why is that the memory was on the in DRM is already mostly file descriptor based. You have to import to a specific file descriptor. You have to export from a specific file descriptor. So it was the best location for us to basically create a page table without a lot of drama. There has been some talk about maybe taking it context-based, which we could do. We could do it on a per context basis, but for the most part, the idea here is it can be anywhere kind of in that spectrum. But when I talk about per instance page tables, or even if I slip up and say per process, I mean per file descriptor. So obviously there's an advantage to having things in a sandbox. One process or one file descriptor can't corrupt the other one. You can't read other people's things. If you have a credit card in a shader, you know, credit card number and a shader drawn in one screen, the other guy can't get it. The other guy can't get critical information. And more importantly, the guy can't corrupt it. He can't show you something that you shouldn't be seeing on the screen. But also as a bonus, this allows for what we call coarse-grained SVA or SVM, which basically means that we can allocate the same address on both the GPU and the CPU, which is used by compute. Compute loves to do this, but other people do it too. If we can't have the ability to provide a page table that's per instance or per process, then we can't do SVA because we have to be able to ensure that each process gets the maximum amount of task space that it can get. This is particularly important for 32-bit, but it also comes into play for 64-bit. So the per instance page tables are triggered automatically in the GPU stream. The command processor can issue a special opcode called SMMU table update, which will do all the nitty gritty of trying to switch over. And we're going to go over that in a second about the exact process. Now, we didn't always have a nice little opcode for it. Back on previous generations, we had to do a lot more inside the code. But luckily, as of 5XX and our transition to the ARM SMMUv2 driver, it's all pretty contained. And so it's actually just a 1 or 2 D words in the command stream to make the transition. So here's a little bit of discussion about how the hardware works. So the key here is that the SMMU for the Adreno GPU is integrated with the Adreno GPU. It shares the same clocks, it shares the same power, and it's only for the Adreno GPU. So there are 2 SMMUs on a modern Snapdragon SoC, but the other one is used by everyone else, and this one is just used by the GPU. So what happens is we start off, we have the SMMU context banks, and we're going to pick a context bank that is going to be used for the GPU. And the reason why for this is going to become clear in a second, but for the purposes of this discussion, we're going to say that the SMMU GPU has gotten context bank 0. And we're going to set up 2 address spaces in the context bank 0. We're going to set up TTBR0 and TTBR1. This works a lot very similar to how a CPU MMU works, where you would have the kernel and the process having different address spaces. This is essential because there are a lot of things in the GPU that require a common global address, such as the ring buffer or the location of the microcode, and there's a handful of other things. So we have to create an initial SMM context with a TTBR0 or TTBR1, sorry, and then program it with all the things that we need to be able to actually run the GPU at a kernel level or at a global level. The next step is that in the hardware, we have what's called an SMMU aperture. And so the aperture basically allows the GPU to see one of the context banks. The reason why it's an aperture and it's limited to 1 context bank is that generally there are other contexts that are running. So we do have a secure context for those who do secure memory. We also have a couple of other ones running some of our graphics management units on the newer processors. And so we don't want there to be the possibility that the GPU could overstep its bounds. If it gets out there and it starts programming other SMMU contexts or other SMMU global registers, you can get yourself into a lot of trouble quickly. So what we do is we create an aperture and we have to tie it to a context bank. Because some of the contexts can be secure, the SMMU aperture is normally controlled by the secure memory in the, sorry, not the secure memory, but the secure trust zone. So the secure world in the bootloader sets the aperture, and then we can't necessarily change it. There are some commands that we can use to change it, but generally it stays at context bank 0, and so we're kind of under the assumption that context bank 0 is what we want to use for the SMMU aperture. So the SMMU aperture is programmed into context bank 0. Context bank 0 is already set up for TTBR1. We're ready to start switching. So what's going to happen is the command processor, it's very simple actually. The command processor is going to come along. It's going to stop the buses. It's going to stop all of this GPU activity and put itself into a situation where it can transition without accessing the SMMU. Then it's going to write the TTBR0 address. So we're going to have a TTBR0 physical address that we've stored for the page table. We're going to put it into the command stream. The command stream is going to write that value into the TTBR0 register inside the SMMU aperture, which then will program the TTBR0 in the context bank, and it will resume the execution. Now we have both the TTBR1 and TTBR0 instance in our context bank, and the process can use the memory that it is mapped into the page table and operate normally. And then the next time we need to switch, the TTBR0 is taken out, the new one is switched in. This happens throughout, until the instance is done. So this is kind of how the hardware works. It sounds simple when we talk about it. I mean, behind the scenes, I think the hardware is probably a little bit icky, but for us, it's basically we have a setup context bank, we program a new TTBR0, and then that gets used for the duration of the operation, and then a new TTBR0 comes after that, and so on and so forth. So there are a few requirements from the GPU side, or at least from the kernel side, to be able to do this. As I mentioned, we kind of need a fixed context bank. Ideally, it's context bank 0. Like I said, there is support for switching it, but that's not available on all targets. So really, if we can get context bank 0 for the GPU instance, then that is the best policy. The next step is to have split page table support, so the TTBR1, TTBR0. This is critical because it allows us to be able to switch page tables without having to remap all of the global buffers, the ring buffer, the microcode, other things, into every page table and have to try and manage that. And then we do need to be able to figure out a way to share the page table configuration between the GPU driver and the SMMU driver. Because what's going to happen is the GPU driver is going to own the page tables that it creates. So using IO page table, it's going to create the page tables, the TTBR0. So it's going to be the owner of the page table. It's going to map directly into the page table, and it's going to have all the information it needs to be able to switch the page table. But in order to create a page table, we need to figure out what the current configuration is. So when the SMMU, when the domain is first attached to the SMMU driver, it will go out, it will create a TTBR1 instance in the context bank, and it will program the context bank. We didn't know what was programmed because in order to get the page tables that match, we need to be able to do that. So we need to be able to grab the page table configuration from the SMMU driver, create our own page tables, and then furthermore, we need to be able to program, or at least let the SMMU driver know when we have the first TTBR0 available. Because if in the absence of a TTBR0, it's a really, really bad idea to have the TTBR0 region active. It's really dangerous. If it's programmed to null, bad things can happen. So when we first create the page table, the context, we will go ahead and set TTBR1 enabled, but TTBR0 disabled. So then at some point, the GPU needs to say, hey, I have an active context bank, we're ready to go, or an active page table, we're ready to go, and it needs to kick the SMMU driver and say, hey, please enable TTBR0. So here's a little bit of a rundown of what the programming sequence is going to look like from between the ARM SMMU driver and the DRM MSM driver. So the first thing is we're going to attach the domain. This is the normal process of an IOMMU. We're going to come up, we're going to detect that we have an IOMMU. We're going to say, okay, please attach our device to the IOMMU instance. So in the ARM SMMU driver, it's going to be identified as we're going to have a compatible string inside of the DT that says we're an Adreno SMMU, we're special. And the ARM SMMU driver is going to look at it and say, okay, this is SID0, which is the stream ID for the GPU. We know that guy, we're special. We're going to go ahead and force allocate context bank 0. All other context banks that get allocated will be allocated from the bitmap, but this one is the one that we know we specially only use context bank 0. So we can guarantee that we always have a known context bank. Then it goes through the normal initialization process for context banks. It'll initialize everything, set up the status, set up the format, and then enable TTBR1 with a page table that is owned by the ARM SMMU driver. So when we create the global buffers, we will program them into the ARM SMMU driver via IOMMU map, IOMMU map. And it will all go through the ARM SMMU driver. So at this point, really nothing's very different, except for we allocated context bank 0, which is a little weird. But instead of using TTBR0, we're using TTBR1 from the ARM SMMU driver. Not much is going on here. So then the next step is we come back into DRM MSM, and it's time for us to create our first instance page table. So the first so what we do is we get the page table configuration from the ARM SMMU driver. And this is done via a shared memory interface that is attached to the device. So when we get the device data, there's going to be a shared memory, like there's a structure that basically is a known private member between the Adreno SMMU implementation of ARM SMMU and the DRM MSM. So we can call a hook in there. The Adreno SMMU will give us the configuration of the TTBR1 that just got programmed. And then we can use that then to create a new IO page table using the IO page table library. And that will give us a TTBR0, or at least a page table with a physical address that we know, and it will have the same configuration that's already been programmed in the Adreno SMMU. Then we're going to send that same configuration back into Adreno SMMU implementation and say, please enable TTBR0. So this will allow the TTBR0 bit to be set. We really don't want to be out there manipulating these registers on our own. That's kind of a bad juju. I know the GPU is going to do it, but we don't want to be doing that inside the DRM MSM driver. We want to keep the register programming all inside of the ARM SMMU driver. So this is why we pass the same configuration back saying, hey, we've got this thing, it's in TTBR0. Would you please go ahead and enable TTBR0 for us? And ARM SMMU says, great. Now, ARM SMMU is out of the picture. Now we're going to do our normal process. The process comes up, it creates memory, it maps the memory, we map it back and forth, all the, just kind of a standard case of memory being created, preparing to do a GPU operation. Then when the instance it goes on the GPU, before we do a submission for that instance, a draw command or something else like that, we will set the TTBR0. So we'll use the opcode inside of the context, or we'll use the opcode inside of the command processor to set the TTBR that we got when we created the IO page table, and set up all the registers and everything, and go. And we'll use that, proceed, do the operations, and then when we're done with our memory, we will unmap it inside of the IO page table. The most interesting thing here is that we will not be able to implicitly do a TLB flush from the IO page table. The reason why is because even if there is a way that we could get to the hooks to be able to do the TLB flush when we do an unmap from the IO page table, but we can't be sure that the power is enabled on the ARM SMMU driver. And what we don't want is we don't want the DRM MSM driver to be allocating and managing clocks. Even though we kind of know the clocks because they're being used by the GPU itself, we don't really want to break that barrier. So when we do a TLB flush currently, we're just going to use what I call the big hammer. It's an IOMMU call, it's an IOMMU API call, IOMMU TLB flush all. And that will call into the ARM SMMU domain and do a flush. So it's a little bit hokey, I guess you could say. It's not as nice as having a more direct TLB flush. There are things we can do in the future. We can construct basically a state machine to help us, because every time we switch to TTBR0, we implicitly do a TLB flush, because obviously the new TLB is in effect, the old one isn't. In theory, it should be doing a TLB ACID, so it should be clearing by ACID. It's not, it's a TLB IL. So we can take advantage of that on current hardware to be able to just basically track memory, know when it got flushed on the GPU, and then just defer the freeing. But that's, there's a state machine there. There's some complexity there. So for now, we're just using the big hammer. Every time we unmap, we're flushing the TLB. It's kind of sad, but I think, to get going, it shouldn't be too terrible. And we do this for every new process. As long as there is an active process, we're going to be creating new IO page tables. We don't have to enable TTBR0 every time. As long as it's been enabled, we can keep it. We just keep creating things, mapping, go. And then finally, when the last page table is freed and we don't have any more things, we will call with a null pointer back into the ARM SMMU driver. So we'll call the same thing that enables TTBR0 with a null pointer. That'll disable the TTBR0 so that we don't have to worry about there being a stale page table out in the world. So this is kind of, this implementation has gone through a lot of iterations. We started off doing, some sort of custom domain design. We went into aux domains. We've just been kind of going back and forth, but eventually we all kind of agreed that this is pretty special for Adreno SMMU. This is something that really doesn't have a lot of interest to other instances or other implementations of an ARM SMMU. So that's why we got into the situation where we started doing some more of this private memory. So already in the ARM SMMU design, there's the ability to create what they call implementation specific code. So using compatible strings, we can jump into things, and that's how you can do workarounds or how you can do things for other processors. There's some out, Qualcomm has a pretty big one. There's some other people have some too. So we just kind of piggybacked on that, and we are creating a compatible string for Adreno SMMU, and it's kicking into an Adreno SMMU implementation that is kind of, it uses, it's built on the Qualcomm implementation, But because we kind of have different parameters and everything, we very pretty much quickly go our own path. There's not a lot of share between the QCOM implementation for the other SMMU and ours. Some of the things we don't need, some of them are workarounds we don't need, so it just kind of we just kind of slide off. So it's QCOM, it's in the QCOM file, but it's in its own world. And then we had to create a new implementation hook inside of ARM SMMU for us to allocate the context bank. So that's pretty simple. If the function exists, we call into it, and then we do essentially the same thing that the generic code does by looking up a bitmap in the bitmap and finding an open page table or an open context bank. The only difference being that if it is stream ID 0, then we know it's the GPU instance, and we'll just return 0. Then the next step would be to create a private interface. So nearly everything else after this point will be through the private interface. There won't be any IOMMU domains, attributes. There won't be any sort of IOMMU API calls. So we had to set up a private interface for the GPU and the ARM SMMU. And it was suggested that we do this as part of the device struct. So we have access to the GPU device or the GPU platform device inside of the ARM SMMU when we attach it. So then we're able to get the device data and then be able to cast it so that we can get to the ARM SMMU data. And then ARM SMMU data has a header file. It's a shared header file. There's a couple of function hooks in there, one for us to get the current configuration, one for us to set the configuration. And I think we also have a cookie in there and some other things to be able to expand for the future. So anytime the ARM SMMU driver is going to talk to the GPU or vice versa, we'll end up using this instead of having to create, a million domain attributes when we don't need them. Then the next step would be to allocate and do split page tables inside of ARM SMMU. A long time ago, Will Deacon and Robin Murphy did a lot of the work to allow IO page table to understand split page tables. So we piggyback on that, and it's basically just a matter of configuring it so that in the hardware, the configuration for TTBR0 and TTBR1 are almost identical. There's one really strange field that gets swizzled for some reason between the two, but we can basically use the IO page table, set up the correct TCR settings, which is the register inside of the page table, and program it. And then because we're a part of an Adreno SMMU implementation, we set up TTBR1 by default for sit 0, and then that automatically goes down into the generic code. So it all just kind of works. We say we want it, and they say, okay, fine, we'll set it up for you. And then we needed to create the Adreno SMMU implementation itself. So we needed to create the hooks that we needed to interact with the ARM SMMU driver. We needed to do the SID matching, and we need to do the private interface for the GPU and ARM SMMU. And then finally, the last bullet here is basically the support we have for A6XX. I skipped over a couple things. As is our want, we like to clean things up as we go along and do some other adjustments. So the full series is listed at the bottom. I think it's actually been updated since, it probably has been updated since this has been recorded. So you can always check to see the latest version, and hopefully we'll see it merge soon. It's gotten most of the reviews. I think there's just a couple people need to sign off. It's a big chunk of code, but I feel really good about what we've done and the implementation we've gone for. I've been trying to do this for quite a while now. I feel strongly, I think that this is, even though the downstream driver has been doing it, I feel strongly that this is something that has an advantage for the upstream GPU driver and all the other things. And so I'm excited to see it kind of come along. But I've noticed over time that it's been difficult to explain exactly what's going on in the GPU and exactly how everything fits together. So I'm glad to be able to provide a presentation to allow people to understand a little bit more about how it all kind of fits together and our intentions for doing this. Because this is kind of weird, it's kind of this, this gray area between ARM SMMU and the GPU. So hopefully it was informative. So finally, we have some stretch goals for the future. One of the other interesting quirks that the GPU has that others don't is that we have multiple things that are accessing the GPU at the same time. And so the GPU could be doing a shader, and it could be accessing memory. And then we have the CP, and it could be doing its own thing, and it could be accessing memory. So if the shader faults for some reason, they're out of bounds or something else like that, if under the current default configuration of the SMMU, we will terminate all pending operations on a fault, which basically is essentially death for the CP, because if the shader faults, that transaction is going to be terminated. But then there's probably a command processor or a microcode lookup pending in the bus, because that's just kind of generally that's how it happens. So if every transaction in the bus is terminated, it basically is a hang. There's just no way to recover. So if you want to be able to allow the shader to fault without really breaking the GPU, we need to be able to allow pending transactions to be retried on the fault. So there's basically there's a setting for that in the ARM SMMU driver, but with our previous implementation, so if we know we're an ARM Adreno SMMU driver, we can set that bit, and we don't have to negotiate with the other ARM clients to allow this. That'll also, this whole interface will also provide us an opportunity to do expanded fault debugging. So on a fault, maybe you want to say where it happened, maybe you want to say what was active at the time, maybe you want to have the client, something a little bit more than there was a page fault at this address, and then you have to assume. And then there's also a desire to be able to stall the GPU on a fault. So basically stop the GPU where in its tracks when a page fault occurs, which would force a dev core dump, which would allow us to analyze the situation and try and determine where the page fault happened. So these are stretch goals. I think that once you have a private interface in place and you have everything that you need to do, it's pretty simple to expand on this. And it's easy to expand on this without having to really modify a lot in the ARM SMMU generic code or in the IMMU API. So finally, lots of thanks. There's been a lot of people over the time that have worked on this. There's some people that have worked on this, the implementation from the beginning. Rob has been really helpful and instrumental in getting some of these going. Robin and Will have been very patient with us over the years. And then special shout out to Bjorn, who I kind of sidetracked one of the things he was working on. I think in the end, everything will kind of come together, but there were some other people that were trying to do some things in the ARM SMMU driver to support some of the targets, and I kind of derailed that, but they've been very gracious in helping me out. And then there's been lots of other people over the years that have looked in on this and given us advice or given us inspiration. So that's the presentation. Thank you for attending.